Hello, yeah. In this video, time series using R, I want to show you how to detect a change point in the variance of a time series. Okay. So let me first set a random seed, and then I'll create a simulated time series, and its variance will change at a time point. So here, n is 1,000, and tau is 600. This is the true change point at 600, and then we have sigma 1 is 1.0, sigma 2 is 3.0. So sigma 1 is the pre-change standard deviation. Sigma 2 is the post-change standard deviation. So then we can create an AR1 series with innovation innovation variance change. So phi is a parameter, so 0.4. Create a YAR as a numerical vector. And then the first YAR1, which is sample one data point from the normal distribution. But the standard deviation is if it's the tau is greater than 1, and then with true sigma 1, otherwise sigma 2. And then the t equal t from 2 to n, we specify this SDT before and after tau. Before tau is sigma 1, after tau sigma 2. And then we calculate the YART equal to phi times YART minus 1 plus a random sampling point from the normal distribution, mean 0, standard deviation as SDT. Okay. All right, then we assign the YAR into a vector of y. So we can quick plot this time series we created and add an AB line. So you can see there's two sections of this time series. At the beginning, it's the variance is smaller, and at location 600, the variance increased. So it's pretty obvious to see in the change point at location 600. All right, and assuming if you don't have the change point library installed, you can run this if statement, and if you have it, it just doesn't run. If you doesn't have it, doesn't have the change point package on your uh, laptop, it will go ahead and install the library. So I already installed the library, so I just load the change point, and then we can detect a single variance change. The option is called the AMOC. AMOC stands for at most one change point. So the syntax is you can use the function cpt.var variance. Okay. So cpt.var of y, and you set method equal to AMOC, and the test.stat is the normal. So it's a normal based variance test. Okay. And then you can print out, you can see the output down there. It uses change in variance and method of analysis of the AMOC, test statistics normal, and use the MBIC. And then the maximum number of change point is 1. So here, change point locations have to be 601. It's a little bit off, but you can see if you look into the data generated, actually, even though we generate the simulated time series, we set the true change point location at 600, but when we really generate this time series, the variance did not really jump very much right after 600. So that's why probably the estimated change point is at 601. Okay. And if you want to really find the location, you can use the CPTS. You put that change var AMOC object into it, and you can actually really print out the change point location. Okay. You can also plot it. This is the change point variance AMOC. It's one step over 601. Okay. But actually, this is probably more accurate. But let's take, what if there may be more than one change point in the variance? Then we have to use another option called the PELT. And the PELT means prone exact linear time. So there was a JASA paper about this method. So it is have some optimal properties, especially when you have multiple unknown change points. So we still use the cpt.var function. So everything the same except method equal to double quotes PELT. And then we can pinpoint the CPTS, the change point location. We can print out the PELT analysis. You can see again, even though it allows to detect multiple change points, it only detected one, which is what's in the simulated time series. Okay. And also you can print out the location. But if you do have multiple change points, this method will allow you to detect those multiple change points and print out their locations. Here's another plot, also very similar to the previous one. Okay. All right. So this is a pretty straightforward way to detect one or multiple change points in the variance of a time series. Thank you for watching this video.